Okay, hi everyone, and welcome back to our session on paper discussion. So this week is slightly different. This week, instead of going through one paper, I'll be doing more of like an overview of a few papers. And these papers are namely from Petar Veličković. I hope I pronounced it correctly. But yeah, Petar is a research scientist at DeepMind, and his research interest chiefly is around this field of geometric deep learning, which infuses deep learning with a graph structure. And he's very interested in using these graph neural networks. Okay, graph neural networks are networks with a graph structure and use neural networks to do backpropagation to update the weights. So he's very interested to use this structure in order to find out whether we can use it to implement algorithms. And this is a very interesting field because we all know algorithms of like computer science. They are very useful at solving tasks and they are very efficient, something that neural networks don't really have. So later we will see some comparison between graphs and between neural networks and algorithms. Okay, but firstly, an overview before we step into that paper of graph neural network, an overview of learning systems in general. So this question has intrigued me for quite some time. And it is basically, how do we actually learn? Like as a fellow human, how do we learn? And what entails learning? Do we learn from what has been pre-built in us, which is nature? Or do we learn from nurture? And I believe the answer that most people have is both. Okay, so yeah, maybe I'll just briefly run through my views on it. Then at the end, we could have some discussion as to what do you think is actually constitutes learning. So firstly, you know, humans have been touted as one of the most flexible learners. Like we can learn different languages. It is said that a child can learn all languages in the world at a young age, because then they can pronounce properly. And also, if we want to do different things, run, walk, swim, climb, we can do a lot of different actions. And it is said that we can learn many things that as long as our body structure allows, we can learn it. So this means that actually the human brain must be quite flexible in learning new things, right? But as you know, with machine learning, if you want to have like graphs with more, did I unshare myself? Okay, if you want to have graphs with like, let's say this is your graph over here. And then let's say you have a few data points. Okay, so this is like the x-axis and this is the y-axis. So in standard machine learning, if you have a few data points, like maybe X over here like that. So if we were to be very fixed, okay, like linear regression, you will be able to find like a straight line here. So this is like the y equals to mx plus c line. Mx plus c. Okay, but if you were to make it more versatile, because a straight line can only do straight line things. You can only fit a straight line. But if you want to make it like a polynomial fit, okay, there's a problem in the sense that if you have more parameters and you only have like a few data points, you will tend to have this trend called overfitting. So overfitting means that we actually fit the training data very well, but it does not generalize very well to the unseen data. So later you'll see in Petar Veličković's papers, he also discusses the trend of overfitting in graph neural networks. And this brings us to this question of, if humans are so flexible in learning, we can learn so many different skills. How do we then not overfit? How do we generalize? You see, like I have a 2.5-year-old child, as a son. He learns how to recognize like a picture of a giraffe from the cartoon book. And then when he sees a giraffe in real life, he knows it's a giraffe. So from cartoon to real life is like almost instant, although he hasn't seen it before. So how do humans learn to generalize so fast from so few examples? And given that we are so flexible, it means that there will be parameters to learn, but maybe not all can be learnable. So just keep that in mind, all right? We have many parameters that we need to ensure behaviors that we exhibit, but maybe not all of them can be learnable. Okay, because if all of them are learnable, we will need exponential amounts of data, exponential in the parameter space, or rather, you basically need at least the amount of parameters minus one amount of data. If you are like doing this kind of like Gaussian equations, I can't remember what's the name for that, but the Gaussian elimination thing, you need like n minus one if there's n equations, something like that. So if we were to think of the data that we need, and if we want to think about flexibility, surely not everything must be learnable. So indeed, the more successful architectures in deep learning so far have incorporated this thing called structural invariances. And what does this structural invariance do? So for example, in CNN, okay, in CNN is having this translation invariance or equivariance. Anyone here want to tell me which part of the CNN actually gives rise to this translation invariance? Jet or Evan, you want to try to guess? Like, how do we achieve this translational invariance in a convolutional neural network? Yeah, you can just type in the chat if you want to. So, okay. All right, maybe I'll just continue first. If you have anything, just feel free. Okay, I see some messages. Yes, Jet says sharing weights by sliding computer. Indeed, the sharing of weights is actually a huge improvement over this thing called the MLP, the multi-layer perceptron. Because if we are to share the weights, imagine your system is able to identify this thing called a person. So if you were to share the weights for your filters and apply it, your filters like from left to right, top to down in the image, okay, like you do a sliding filter here and the weights are the same, it means that we can recognize like a human on the left of the image, on the right of the image, and so on. So regardless of where the human appears, your neural network will process it the same way. Okay, so this idea of if the person shifts and you will still be able to classify it in the same category, this is the idea of translational invariance, because regardless of how you translate your objects, you will actually get it in the same place. Oh, sorry, you will actually get the same classification. So in some sense, there's also translational equivariance. If let's say your output is a bounding box, okay, then basically with the human shifted, okay, I can actually give the bounding box at this position instead. So equivariance, because if my input shifts to the right, my output also shifts to the right. Okay, so typically filters, these two words are associated with them, invariance and equivariance, depending on what's the output. The translational invariance part comes from this max pooling, because in this case, when we have like the human on the left, human on the right, if let's say your filter is like this, 1, if there's a human in the picture at that position, if your filter is like that, 1, 0, 0, 0, and then if there's another filter like this, 0, 1, 0, 0, it will all be classified. If you do max pooling, it will all be classified to be 1, which means that if the human is on the left or human is on the right, it will still be classified in the same way. And human on, yeah. So this is translational invariance. Okay, and the first part is translational equivariance. And all this actually means that we don't need to learn from so many samples. And that is the beauty of like a convolutional neural network. We can train it on, like, for example, the MNIST data set, and then we can use it for like different kinds of tasks. For example, recognizing digits on your envelope, recognizing digits on your buildings. As long as the numbers look similar, you can actually translate, or you can actually apply on different data sets. And you can also, if your training data has only a 2 at the top left, you might be able to generalize to the 2 at the top right, 2 at the bottom left, without even looking at all those examples. So it does help speed up learning. The other way that we can actually speed up learning is actually, like, for example, the more popular architecture, the RNN. Okay, nowadays is the attention layer for transformers, but RNN is called recurrent neural networks. And one good thing about recurrent neural networks is basically you just have a function here, a function f that takes in the input at the current time, xi, plus the hidden layer output of the previous time step. So you can have this hi plus 1 equals to this. which means that whatever output came from the previous time step, plus the new output and the new time step, you can actually use this to make a new prediction, H as well as basically the H. Depends on the kind of recurrent structure. But this means that we can actually have this function repeated as many times as you need, and you just only need to learn this function. And this is very useful because, for example, let me give you an example. If we have the sum function, okay, that takes in the outputs like x1 and x2, that you want to sum both numbers together. So one way to do it will be to memorize the output like a memory table. Like you have numbers 2 and 5, you add up, becomes 7. Okay, the other way to do it is you start with x1 in memory, and then loop x2 times, and then sum, and then add, and then perform this x1 equals to x1 plus 1. So this kind of structure where you do this kind of for loop is quite typical in programming, and it's actually quite related to this function here. Can you see that? If your function here is basically this function, let me just write down this function. If your function here is basically this function, fx, basically the input here will be like the counter to your loop. And then let's say x2, and then this hidden state will be the memory x1. You can actually just be, you could do this like that. And then basically the x2 can be like a sort of indicator to see whether or not your sum is over. So like instead of having here, so let's say you have x2 over here, you can do like x2 minus 1 over here, x2 minus 2, and so on until when you reach 0, then you terminate. So this can be like your indicator function. Yeah, so we can actually make recurrent neural networks do a for loop. That's pretty amazing. And that also means that, can you all see that if we were to do this kind of way of doing a recurrent neural network, we actually just need to know how to add 1. Okay, then we just need to keep repeating this process of adding 1 in order to find out the sum. So you can do that for any arbitrary 2 numbers, x1 and x2. You don't have to have a memory table. You just keep repeating this same method. And I will call this method now an algorithm. So you can see that RNNs, the structural invariance over time, could be a building block for like a sequential instruction that goes through, that loops over time. Okay, so this is one of the structural invariance, and it can actually help to speed up your learning, because by just learning one thing, which is learning addition, you can generalize to any kind of summation over any number of variables. So that's the power of it. Jack, you agree with what I just said? Or Evan, are you okay with what I just said? Okay, let's move on. So these algorithms, these are very powerful tools. Okay, algorithms can actually tell you how to process your data. It encodes a whole series of instructions from the data processing part, and then after that, how to manipulate your data. So some of the ways that this kind of algorithm might be present in our biological life is perhaps epigenome. So an epigenome is basically the way that the genome is expressed in a cell. So you all know that all cells have the same DNA. It depends on the regulating factors or the epigenetic factors that actually decide whether a cell goes become a brain cell, skin cell, heart cell, muscle cell, and so on. So how do we know what this genome should be expressed? So perhaps in the DNA itself, there are some rules that say that, okay, if you see this and you don't see that, then you become a brain cell. Or like if the certain concentration gradient is above a certain amount, you become a skin cell. So there could be some things like this. There's many different factors involved. And all this can be encoded as part of like an algorithm that can make our bodies work. Okay, how exactly this algorithm is, or what exactly this algorithm is, we don't really know for sure because it's so complicated. But this is an example of how algorithms might be used, okay, in real life. Okay. So the next thing is like, how should our eyes generate this internal representation of vision? So there have been cases where, like, you know, when you see things, are we able to see every single thing? Actually, not really, because we are limited by the structure of our eyes. Later, there will be a slide on that. We cannot see things like UV light, because that's beyond the spectrum that is visible to us, beyond our visible spectrum. So again, what kind of light we can see, all this might be also encoded by an algorithm that tells the cell what to do. And I feel like this algorithm has an even stronger bias than structure itself, because structure just tells you how to like encode the filters and so on for CNN, or RNN should tell you like how to use that function again and again over time. But this algorithm tells you everything from step 1 to step n. You do follow the algorithm, and then you will get something out of it. So algorithms are quite generic and quite powerful if they are done well. So in the biological example, this you can see here, this is the cochlea, which is the ear. There's cilia in the cochlea here that vibrates as sound enters the cochlea. So as you vibrate earlier, it represents higher frequency. And as the sound attenuates as you go through, if the hair vibrates near the end, it's of a lower frequency. So in some sense, because of the structure of the cochlea, it mimics what engineers have typically done, called the Fourier transform, where we transform a time-based signal into frequencies. And all these are just done through the structure of the cochlea, just because it is a long channel. And based on the hair vibration of the cilia, you can then break down into frequencies. So all this could be encoded as an algorithm. Like for example, if you want to make this an algorithm, it'll be like, you start off with like 20,000 hertz. If 20,000 hertz present in the sound, then the memory for 20,000 hertz plus 1, or the input, then you decrease the hertz to like 19,000, 18,000, and then if it's present in the sound, then you plus 1 to that memory or to that input. So you can do that as an algorithm. Okay, of course, nature has its way. All this already in the structure of the ear. For the eye, you can see that when you enter the light enters the pupil, it'll be reflected like that, and then it goes onto the retina. And on the retina itself, there's like cones and rods that basically activate when it's like you see a light or you don't see anything. So these cones and rods actually affect how we perceive things, because it is through the inhibition of like the cones and rods amongst the nearby cells, then you can see like contrast light and dark and so on. So this is quite important, because this actually represents like how we see things. So people have also found out that we tend to see things, we tend to view brightness as more important than color. So because this might be the nature of the cones and rods inhibiting different patches of brightness or darkness. So there's this image formatting, I think it's called PNG or JPEG, sorry, it's JPEG. Yeah, the JPEG image editing tool, they actually preserve brightness very well, but they don't preserve the color information that well. And it turns out that we don't really tell the difference. So brightness is quite important for our eyes. I think it's brightness. Okay, so I'll just double check this again, but I believe this is related to the cones and rods of our eyes. And again, this shows that structure helps in processing this complex information. So in the computer science example, we have this thing called the Dijkstra algorithm. And in the Dijkstra algorithm, what people do is like this. So you want to find the shortest path from starting point to the ending point. So how should we go from the start to the end? So one way is just to try out all possible routes, and then you just do a Monte Carlo search, and then you try to see what's the shortest route. Yeah, but that can be inefficient. So Dijkstra came out with an algorithm that is very efficient, provably optimal way of getting there. So instead of just doing a random thing, what we do is we first store all the vertex into a set. Okay, and then what we do is we just start off with the smallest weight. In this case, the start has the smallest cost, okay, smallest cost because the cost is 0. Then we evaluate all the neighbors here, and then we update the neighbors' costs. So in this case, initially all the neighbors' costs, the distance is infinity. Now we update this to be 2, 3, and 6. And then immediately we can take away this node. Then we take the next lowest cost neighbor in the queue. In this case, this will be C. Then we look at all the connections. Evan, I think you are familiar with this because you have been doing LeetCode as well. So this is a LeetCode example of a graph. Yeah, so this one you become a 5. This one is a 4, but 4 you don't update it because 4 is smaller than 3. It's not the minimum distance. So then we add this D to the buffer. Then we go to the next minimum node. In this case, the minimum node is 3. Okay. Okay, so the previous step we already take out this. So 3, you can add 6 here, you get 9 here. 3 plus 1, this gives you 4. So we update this because 4 is smaller than 5. Okay, then we can remove this. So now we have 4, 9, and 6. What we can do is we can start with this 4. We go here, we get 8. Okay, and we can just remove this. Now we have 6, 8, and 9. We can go to the 6. Okay, we can start with 6, add 2, 8. So this is the same as the previous one. So we can still take it out. Then finally, okay, we still have this B over here because the queue is not empty. Okay, of course, if you do like A-star algorithm, you will know that this is actually higher than 8. With a non-negative cost, you can actually terminate the algorithm when your node, okay, has already a cost that's higher than the goal cost. Okay, but for completeness, this gives you 10, which is larger, and so we don't update it. So from this simple algorithm that we just do a loop, we can tell that the optimal path is like this. Okay, 3, 1, 4. Okay, let me just undo, because there are 2 optimal routes as we saw in the algorithm just now. One path is like that, and the other path is like that. So this tells you a very complete and very comprehensive way of finding out the shortest path. And this is an algorithm that can be encoded, perhaps in a neural network, or maybe this might be how we reason, although I highly doubt it because I don't think we reason like that. Yeah, but this is an efficient mathematical way to find the shortest path from a source node to the end node. So why do we want to use like neural networks to approximate algorithms? Okay, so this is Petar Veličković's work, and he has been pushing quite hard on this, how to use neural networks to accomplish what an algorithm can do. So early on, if you buy what I just said, an algorithm is very powerful. With the algorithm alone, you can tell a set of instructions of how to process your data. So if I were to be able to get a generic algorithm that can do what deep learning is doing now, like for example, do the translational invariance of a CNN, you will be using algorithms because algorithms are 100% guaranteed to work in the conditions that they are set. Okay, but you will require very specific like inputs. Okay, you will generalize very well to all kinds of problem sets like the sum of 2 numbers. You can generalize very well to any 2 numbers, which is what neural networks may not be able to do. The neural networks can do some, because in this case, the nodes, they actually sum up the weighted sum of your inputs, so they can do some. But if your neural net is supposed to do like modulo or multiplication, I've done experiments on it, it will face problems. So an algorithm will not have this issue because you can already tell the algorithm how to multiply a number. You will guarantee the algorithm to be correct, which is a good thing. For cases like self-driving car, you want to make sure that you don't hit the pedestrian. If you can make this into an algorithm, it will be way more efficient than neural networks and way more safe also. Interpretable, of course, because we already know the steps. You don't need the training data. Okay, that's if you already know what you need to do for the processing of your inputs. But however, it's not robust to task variations because the algorithm is typically task specific. Okay, but neural networks, what are the benefits of neural networks? It operates on raw inputs. So even if the input is a bit noisy, you can still like sort of generalize to still make it work. Generalize on noisy conditions, which an algorithm may not be able to do. Okay, unreliable when extrapolating. This is a very big point. Okay, neural networks typically only do well within the training distribution. And that is actually a huge issue for even self-driving cars, because if the training distribution is outside of your, if the test distribution is outside of your training distribution, you will have issues to apply what you learn to the outside world. So a case in point is Tesla cars. They have been trained with the stop sign of a certain diameter, of a certain length. And basically, when deployed to a certain state in US, the stop signs are actually smaller. And because of that, the Tesla car stopped much earlier. or is it bigger? Basically, based on the different size of the stop sign, the Tesla car actually stopped earlier than the required stop. But that's a small thing. But this shows that if we were to use neural networks to do decision making, you better make sure that the test distribution is very similar to the training distribution. If not, you might get unreliable predictions. Okay, lack of interpretability, that's one huge thing with neural networks, because you know the weights, but you may not know what they represent. You need a huge training set and a lot of training time. But you can use this neural network across many tasks. It may generalize across tasks if you train it well enough. So there is some benefit to infusing both the generalizability of neural networks to cater to like most situations, and the specificity and the accuracy of algorithms. So would it be nice if you can blend both algorithms and neural networks together? So let's see how we can do this. Okay, before we go into Petar Veličković's work, let me just share with you my thoughts on how learning takes place in our brains. So firstly, we have the input. And then I feel like we do some pre-processing that is fixed. Like for example, the cochlea does it through frequency by the vibration of the cilia. Okay. And the eyes, the retina does it through cones and rods that react to dark patches and bright patches accordingly. So all these algorithms sort of bias the data that we see. Like we can only see, maybe we can only see frequency after we go through our ears. Yeah, so there's a few things that could happen. Yeah, so there's a few things that could happen here. And so I feel like there should be some fixed algorithm here, because if we have a very variable structure to learn this way of processing, you will need a lot of data to learn. And that is something that humans don't really have. We don't actually need that much data to learn something new. Then we also do this learning process using some fixed structure. So this is my thoughts on like how we learn, because if we don't have this fixed structure, again, we will need a lot of samples to learn. So you talk about data efficient learning, you cannot have a variable structure, because this might actually mean that you will need a lot of data to do so. And lastly, we have the output over here. Okay, so that's more or less what I think is happening. Let's now see whether neural networks can actually approximate algorithms. So the first paper I'm going to talk about is this CLRS, Algorithmic Reasoning Benchmark. So it is in ICML this year. So let's see what this paper talks about. So this paper basically wants to benchmark the performance of algorithmic reasoning procedures. So for example, sorting, searching, dynamic programming, and so on. So the typical competitive programming problems. So instead of using algorithms to solve it, we try to use neural networks so that we can perhaps learn what is good in the neural network, which is the generalization abilities. We might be able to learn these generalization abilities if we infuse whatever we know about the algorithm inside the neural network. So let's see whether the neural network can solve this kind of algorithm-like problems. So this CLRS 30 is a set of 30 tasks, and some of the tasks are, for example, insertion sorts, string matching, which is like the longest common substring, greedy task scheduling, like basically how to find the shortest time to arrange all tasks if there are some prerequisite, like you need to finish A1 before A3 and so on. So this is used in a lot of planners right now. And shortest path, like the Dijkstra algorithm from start to end. And you see, this might also include negative weights. Dijkstra actually works also on negative weights. Yeah, so this is the, well, actually not really. if Dijkstra has a cycle, it doesn't work, but negative weights, I believe it still works. But in this case, you see the graph contains a cycle. And if it's a negative cycle, you will not get Dijkstra to work. Let's see whether there's a negative cycle here. -3, -2, 8. Okay, there's no negative cycle, so it's still okay. So these are some of the problems that you can use the algorithms to solve. And so what architecture is used to solve these problems are typically known as this thing called the graph neural networks. So I actually given a talk on the graph neural networks before, but as a brief recap, this is what a graph neural network is. So graph neural networks, firstly, you have a graph, and actually this graph is generic. CNNs also have a graph, but the graph is very rigid. So basically, like for example, in CNN graph, it's a graph of pixels. So I just drawing the pixels here. Like one circle is a pixel, and then the edge is the connections. So you can see that this is like how a graph typically is. Yeah, maybe I erase away this. So in a patch, for example, in a filter, you have all these nodes here, which represents the pixel values of the filter. And then you can see that in a CNN, all of these are linked to like maybe the center node because your filter is applied to the center. So this, basically these weights here can also be represented as a GNN, as a type of GNN, where it's connected to the center pixel. So given graph representation and given the input space X, as well as the adjacency matrix A that tells you like what node is connected to what node, we get a certain graph. We apply a GNN, which is very similar to a recurrent neural network. Okay, we first transform the input space into a latent space H. And then we just keep iterating over the latent space as many times as we want. Over here, they call it different layers of the GNN. This is similar to like processing over time in the RNN. You just keep processing the latent space where you exchange information between the nodes or edges or both. And then eventually your hidden space, you can then do a node classification using the latent variable H. You can also do a graph classification by summing up all the latent variables, or you could do a link prediction by taking like node A, node B, and the H between them. You can then use that as a function to do a sort of link prediction. Like for example, chemicals, you want to find out whether a certain bond is present in a chemical, you can use that. So the main three flavors of GNNs, this is from Petar Veličković slide. I like it a lot. So first is convolutional, where you actually have, that's why I drew earlier, all the like the filter weights for all of these pixels, including itself. So you can just sum up all this using an translational invariant, permutation invariant function here to sum up all the representations of the nodes times a weight plus itself. And then you perform another function here. So this is a convolutional structure where basically we actually have already this given weights here for each of the representation. If you want to make it more generic, we, instead of having a fixed weight here, which is the fixed filter weight, instead of having this fixed filter weight, we have a dynamic weight here. There is assigned based on perhaps similarity between this input and this input. Like the node in question and its neighbors, how similar are they? You can use things like cosine similarity, or you can use things like attention. So in attentional neural networks, this is actually invented by Petar Veličković, but this actually uses the self-attention method of a transformer in order to gauge how much of a weightage you want to give your nodes. And all this actually sum up to 1. Okay, so based on the attention, is like the amount of attention you want to give your neighbors. So all this attention actually sum up to 1. So this is the attention method. The last more generic method is, instead of just restricting it to a linear combination of your input features, why not we just let it be an arbitrary function? So message passing is like that. You actually have a way to find out the message between your source node and your end node. And then using this message here, these are your messages. Okay, you can then use your message to update your latent variable itself. So this is the most generic. So in terms of generic methods, convolutional is more limited. Attentional is more flexible. Message passing is the most flexible, because message passing, you can parameterize all the kind of interactions you want between like the start and the end. As long as they can be represented in a neural network function, you can do whatever you want. Like over here, you are only allowed to change this C, this weight here. Here, you can let it be more dynamic, it's more flexible. Here, you can do whatever you want. You can do like a non-linear function as well. Okay, as long as it's representable in a neural network. Okay, with that in mind, let us take a look at how this paper tries to tackle this problem to solve algorithmic reasoning using neural networks. So typically, this is the encode process, decode process of how to how to encode an algorithm into a neural network. So firstly, we have this setup where we have this inputs X. Like for example, if it's a summation algorithm, the inputs X will be like number 1 and number 2, like 2 and 5 to sum up. Okay, we have the edges. In this case, like for example, the summation one, it's like fully connected, the two nodes linked together. So, but for some other problems, the edges might be different. The edges might be like the adjacency matrix. So typically in the case for the algorithms, all of them are fully connected graphs, except maybe in graph algorithms, where you have the adjacency matrix, then you use the adjacency matrix. Okay, then you have this linear layers where you actually represent the input into like maybe a lower or higher dimensional space, depending on the problem. Yeah, so this is the way we represent. So we have the inputs, the node inputs, the edge inputs, and we have the graph inputs if we need to like form the overall graph as an information for that particular problem at hand. So then this will be fed through a processor network. And this processor network will basically be a GNN in this case. So we basically do a process whereby we generate this Mij to be a function of all the latent variables earlier, Hi, Hj, Hij, which is like the, I think Hij is the latent representation of like the I and the J nodes. Is here, this one is the H basically, the latent representation of the H, and the Hg is the latent representation of the graph. So with a function of this 4, okay, normally we don't need the graph. Most problems don't need this H thing, except, but basically, to be generic, we include all of them in one equation like that, and then we calculate the next latent variable Mij. This is like the message passing, and then the next message will be like an equivalent, a permutation equivalent function of all the neighbors' messages. Okay, then your latent space Hi will then be a function of your previous latent space plus the message. So it's very similar. You can treat this actually as whatever you talked about earlier here as a message passing. This is actually very similar to message passing. Okay, except that we have more information. Here we omit the edges and we omit the graph information, but here we add it back here. It's the most generic equation for graph neural networks. And basically the idea of encode-process-decode will be encoded into a latent space, process it using the GNN across this latent space, process the nodes, the edges, and basically process this over as many iterations as you want. Typically in the algorithm papers, they have this termination criteria where basically it's a binary predictor value. If it's 1, then you terminate. Yeah, so that's typically how they do it. And then after that, you take these process messages and you decode them. So this really means that whatever you want over here, like maybe we take the Hi, the node representation. If we want to find out like the sum of 2 numbers, we can just take the node representation of maybe the bigger one, because after you sum it multiple times, there'll be one latent representation that is the biggest. You can take that, and then that will be the sum. Okay, of course, you take that latent representation only after you terminate your loop, after you terminate your GNN. So let's see what are the results of trying to use neural networks to encode algorithms. So the main thing for they actually did on 30, but these are the main things here. You can see that if you just pay attention to this MPNN message passing and the GAT, this orange line, you see that actually the red and orange appear like almost at the top all the time. Like you see, all of them are all at the top. I mean, I'm not going to go through each and every one of them, but it appears that message passing neural networks and GAT perform the best, and they are very close to the score of 1, which means that great. The neural networks have the capacity to learn an algorithm, which is promising, because then we can use this neural networks to generalize across different kinds of inputs. Okay, and one key thing of concern, okay, which is also mentioned by Veličković, is that this high number of parameters that are used in the network may actually lead to overfitting the data, because this means that we have, as I mentioned in the first slide, we can have a lot of parameters and we sort of overfit the training data, which means that it doesn't generalize to the test data. So let us see whether or not this overfitting trend is indeed present. So we go to the out of distribution results. And over here, instead of just the graph, we can just take a look at like the percentage of soft. Okay, and you can see that overall, this is the pointer graph network, which is basically a modification of like an attentional-based network. You have each node pointing to another node. So like, for example, if you have like a graph structure that you need to traverse nodes in a certain order, you can actually have this where I believe the next node is given by an argmax of maybe an attention function. Yeah, so basically this next node, this pointer value that each node stores. So maybe like node 2 can link to node 5 and so on, or link to node 1. Yeah, so this pointer network can like store just like one node that it links to next. And it can serve as the way for the neural network to know what node to go to in a dynamic way, because the node that it points to can change. And if you look at the overall like average solve rate, the pointer graph network works well. It actually solves only half the problem, but it's quite impressive because this is out of distribution results, which means that there's some learning, just not very strong learning. And the win-tie loss is basically like how many times the algorithm wins, how many times the algorithm ties, how many times the algorithm loses across all these 5 algorithms. You can see that this is still the best. Okay, in terms of the ratio, it wins the most. 8, 6, 16 actually is very close to message passing if you look at it, just that it ties more. So this pointer graph network has been actually shown to be more generalizable, likely because of this way that it can point to different nodes based on the data. Okay, but this is more constrained because it only points to one node. Message passing or like GAT, you might be able to use attention-based methods or use like a message passing method, but this actually may have too many parameters and not as few parameters as like this pointer graph network. So it can be seen that actually, if you restrict the amount of flexibility, you might actually generalize better, which is in line with my intuition earlier, that you need like some kind of fixed structure in order to learn with fewer data. Or in this case, in order to do out-of-sample generalization, you need the right structure to carry over so that your insights or your methodology can still work even with different data. And from these results, we have another thing that we can see. We can see that this dynamic programming and this greedy algorithm seem to be the best performing problems. You can see that typically they score very well. Okay, this wasn't in the paper, but this is what I noticed. And I feel like this may be the case because like dynamic programming, typically what you want to do is like, for example, Fibonacci sequence. What you want to do is you want to do like this. Fn equals to, if you know Fibonacci sequence. Evan, you know Fibonacci sequence? Fn equals to Fn minus 1 plus Fn minus 2. So you can define this recursively. Okay, and I mean, if you were to like update these values, like through a for loop, this actually is kind of similar to the GNN structure or RNN structure. You can do it over a for loop. Anything that has a for loop and a similar update equation it can be quite easily doable over a GNN or an RNN. So this might be why dynamic programming, because it's just an update equation that is the same over multiple time steps. So it seems to work pretty well. Greedy, why greedy works well? Because of like the permutation invariant function or permutation equivariant function. I think it's permutation invariant, which is this permutation invariant function here. This one, which means that no matter how you permute your nodes, the output will actually it's permutation equivariant, because your output latent variables for your nodes will have a similar form, just that they might be rearranged according to your permutation. So it's permutation equivariant. Okay, permutation equivariant function here. This function here, okay, this may actually be the reason why it does so well for greedy algorithms, because you might have a max operator where you take the maximum of the latent variables. And in greedy, normally what we want to do, we want to optimize, we want to have the best performance. So we typically maximize over an objective or minimize, but you can always represent the minimization problem as the negative of the maximization. So it's still possible. So this maximum operator might be similar to how greedy works. So you can see, actually it's quite intuitive to me that like this one and this one did well, and that may actually point out that that is the structure of a GNN. A GNN allows for repetition through like a for loop kind of structure, which is why dynamic programming can work. A GNN allows for aggregators like maximum, which is probably why greedy can work. Graphs, I would expect it to work pretty well also, but it doesn't work too well. So I need to see what kind of graph problems that, because graph neural networks is on graphs. So one might naturally think graphs do well. It's not the case here though. Divide and conquer will be hard. Okay, divide and conquer because you need to know how to divide. So this is not very intuitive. You can see that they don't do very well here. But surprisingly, this pointer does pretty well. Yeah, not too bad. Yeah. Search problems are typically difficult, but still okay, because I guess there might be some ways of utilizing the GNN structure to do it. Sorting and strings are very bad. Okay, maybe, but except for memnet, you can see that sorting, because you need to know like how, like insertions sort, you need to know like your rearranged sequence of array, what is the array state. So you need to carry over that state, which is not inherent in the GNN architecture. So memnet may be able to bypass that because they can store the memory of, they treat the nodes as memory and the ages as the operations. It's either or, it's either the age as the memory and the nodes as operate, but basically they can treat the graph structure and store as memory some part of it. So it points to the fact that sorting and strings may need some better way of representing, like maybe the base state array. Okay, we cannot just use the neural network weights because they may not have the required information that these algorithms need. Strings also, like longest matching substring, you kind of need to have memory, and you also need to have some form of like greedy algorithm. That is not easy actually for string manipulation. It's one of the harder problems, but typically is like one of the beginner problems that appear in the competition. But in order to do the strings, because there's so many different kinds of string problems, it can be difficult to do it. So yeah, all of the algorithms didn't do too well. I think you need memory, plus you need some form of intuition. So it's not easy for a GNN to solve it. So let us take a look. Okay, we're going to end this soon. Okay, this took longer than I expected. But this is another paper that is also quite recent in NeurIPS 2021. Like, how can we transfer learn this algorithmic reasoning? You know, we can transfer learn images, transfer learn like audio. Yeah, how can we transfer learn an algorithm? Like, you know, one algorithm, can you learn a similar one? Let's see. The answer is no. So this points to the fact that the transfer learning is not natural for algorithm problems. So like, for example, they train the prim shortest spanning trees algorithm to the Dijkstra shortest path algorithm. Very similar in nature, although they do different things, but the way that prim does it and Dijkstra does it is similar. It's just solving different problems. So can we use the same procedure? The procedure-wise is similar. Can we use the same procedure? We learned the prim algorithm already. Can we learn something else with the similar procedure? So can we learn a new thing that is not too different from the old one? So one thing that they found out is that the more expressive the model, the less it generalizes, which is what we discussed earlier. Okay, we have too many parameters, you don't generalize that well. If you freeze your weights or you fine-tune your weights, they also don't really help with the transfer. In fact, sometimes it worsens the performance, which means that maybe the way we represent algorithms as a graph is not the way that, the way that we represent algorithms in a graph neural network. Maybe that's the wrong approach to do it. Okay, because the algorithms itself have some form of procedure, like take this number and add to another number. So all these kind of procedures may be very difficult to do with just a neural net, because a neural net is meant to generalize, not really do all this fine-tuning of very specific things. So it's very difficult for a neural net to do. If you just suddenly change the weights, you freeze the weights, or you fine-tune to a different problem, you might actually lose out on whatever you learned in the previous problem. So it's not easy, because traditional transfer learning techniques do not work. Okay, which also points to the fact that maybe algorithms, you need something more than a neural network to actually solve it. Maybe you can't even use neural nets. Maybe you have to use, just memorize the algorithm itself. So yeah, there's some insights that we can perhaps discuss later. Trying to extract these subroutines does not help with the transfer. Like, you want to take the shortest path you want to take like the for loop, where you take the minimum vertex. You try to transfer learn this whole thing unchanged, freeze the weights and transfer to a new architecture with new inputs and outputs. It actually doesn't really help. So this is quite funny, because one would expect that with the subroutine you can actually learn better because you know how to do the for loop. In the paper, they say that maybe because it's too well trained, the neural net does not know how to learn from this data, does not know how to interpret this data. There's something like a mismatch between the source and the destination. Like the source might do it really well, but is using like system A. But you go to the destination people are very used to system B. Then when you see a system A routine there, it's like, hey, what do I do with it? So just transferring the weights alone may not really help here. The only thing that worked that they found out is this thing called multitask learning. Technically, it's not really multitask, okay, because there's only two tasks, one thing, and you are technically using the same procedure for your first algorithm. So for example, you have a base algorithm B, and you have an unknown algorithm, target algorithm T. So what we do is we will use the processor, which is basically the GNN, how you process your information. You use the same weights as both T and B. Okay, we know the procedure for B, so it's kind of giving the same weights to B. But the only thing that's different is that the latent space representation of T is different. So it's like giving the steps to solve it, but letting the network interpret the actions, inputs and outputs. So early on, we have this subroutine thing that didn't really work, okay, because we maybe only transfer part of the model, system A versus system B. So in multitask learning, we just transfer the entire system altogether. So I transfer system A from this algorithm all the way to the other algorithm. And the only thing that changes is the input and output. And it works if we do it. And that means the process must be exactly the same. Okay? The processor must be exactly the same. The process of doing this must be exactly the same, which also means, in my opinion, again, I think I may be wrong here, but I feel like this means that we cannot transfer learn, because you have to like sort of spoon feed the entire set of instructions in order for it to work. So there may not be cases where the algorithm is exactly the same. Yeah, so like although one part of the algorithm might be similar, it shows that it's not easy to like just bring over one part of the algorithm to another. The whole algorithm needs to be there. The whole complete package needs to be there. So yeah, that's quite interesting. I really like their work. It just makes me think, what is the best way to do all this? How to do learning? So I look at all this and I think about how to do learning after this, and I came to some form of conclusion. So this is my opinion. Okay, so my opinion is that the neural networks, although very powerful in generalization, but okay, it might also be able to replicate algorithms like in the CLRS benchmark, but it must do so with a lot of guidance, a lot of hints as to the structure of the problem, like how many times you do the for loop and so on. This whole algorithm process is not innate to the neural network. I don't think neural networks actually do this sequential tasks or parallel tasks. All this needs to be like pre-programmed. Like a lot of the successful neural networks, like stable diffusion, CNNs, the algorithm to process the data, like for example, the filters, stable diffusion is some objective function that is pre-programmed. All these are actually like human defined. The neural network itself does not naturally come up with an algorithm on its own. I mean, the neural network itself, the processing is an algorithm, but in order to pre-process the data in the right way, it's not innate to the neural network. You actually need to do quite a lot of work. So this is my view. My view is that the neural network perhaps is not designed to do algorithms. Okay, but how do algorithms come about then in nature? Like the cochlea and the retina, how do we know how to process our inputs? So what I feel is that nature does it in separate parts. Oops, nature does it in separate parts. And these separate parts really just come together in a way that each part may just know how to do its own things. Like the cilia only knows how to vibrate when it reaches that kind of resonant frequency. And then the cochlea itself only knows that it needs to curve. And then the hair needs to know where to put on the cochlea. And then all in all, the whole thing needs to form in the right place. Maybe it's in the epigenome, maybe it's in the DNA itself to identify the structure. But all these separate parts coming together, each with their own purpose, they may not even know each other's purpose, but each with their own purpose, come together like a soup of agents working together, can perform an algorithm. So it means that maybe the algorithm could be a result of something that is like, for example, genetic evolution, or sorry, natural selection. Evolution might come up with a way that puts things together, and somehow this works and this was selected for. So I think there's something to do with natural selection here in order to implement the kind of algorithms that we want to see in, for example, the human body that works pretty well. After all, the eyes took a few billion years to develop. So yeah, Fei Li is a fan of vision also. So she also talked about like how this natural selection might play a huge role in the fitness or the evolutionary advantage of humans and other species with eyes. Yeah, so this natural process might take very long, but the whole algorithm coming into place is definitely something that is probably the reason why humans are so advantageous in the environment right now. So how exactly is it to actually get that structure straight away? We don't know. Yeah, but I feel like natural selection has a huge part to play, or evolution has a huge part to play in coming up with a viable structure, or viable algorithm that can process our data. And also one thing for academia is that we like to pursue this thing called optimal. But in nature, I don't think nature designed us to be optimal actually. There's quite a lot of things that we don't really understand about ourselves, like why do humans have an appendix? What's the use of it? Yeah. Why do we have neurodegenerative diseases? What's the use of that? So how are all this part of an optimal plan? Okay. The simple answer is maybe we are not designed to be optimal, but we are designed such that we can survive well enough in our environment. And that's why we are selected for in order to replicate. So, I mean, I'm not saying that natural selection is everything, but algorithms and the way that nature processes the data in species can be quite different. Okay, in algorithms that you see, the Dijkstra, or this, we focus on mathematical rigor, provability, optimality, which takes a lot of iteration and a lot of brain power of many talented people to come up with. But nature may not be doing all this. We just might be doing something that works, and because it works well, we see it more often. So I still feel like maybe the secret to this kind of pre-processing from in order to process very complicated data in a simple way, or in a very competent ways, like an algorithm, will be to do this kind of multi-agent process where you have different agents coming together and create like a performant, but maybe not optimal system. And then what you need to do is to just choose the system that works well. So perhaps we've been trying to do the algorithms from top down, which is basically replicate the entire algorithm itself. But maybe we can look at the bottom-up approach where we have different competent parts and then we just mix them together, see whether it works, see what happens. Yeah, and yeah, I think maybe nature may be not as efficient as some of the algorithms, like common substring or this kind of things, that it may not be as efficient. So perhaps trying to replicate the computer science algorithms may not be like the right approach to nature, but it might be a good approach to do like optimal data, like AI. You want to do very, very competent AI, maybe it's the right approach. But I'm just thinking that like all the difficulties with transfer learning, like you change one component, it doesn't work already. Yeah, it kind of hints that the whole system must be there together, and like a whole performance system maybe is better selected from the bottom up, although it might take years and years of selection. Hopefully computer processing speeds will be faster. We can do the iterations faster for like natural selection on the computer. And that some future directions, I think like this whole algorithmic reasoning might go is like finding out like multi-agent systems. Like you have a memory module, you have GNN, maybe a GNN, multiple GNNs, and then you just mix them up together and see whether it works. And then if it works, then it works. And maybe we should have other benchmarks other than like algorithms. Maybe we can do something like Fourier transform, like the cochlear theater, through this random soup approach, whether it can generate that. Or similarly, like for example, our eyes. Okay, right now we have convolutional neural networks that try to mimic what the visual cortex is doing. Yeah, but how exactly did this come up? So that's an open question. But my feel is that with enough experimentation, perhaps you might stumble onto the right structure. Yeah, of course, all this, you need the right components to do it. And these components should have some form of structural bias so as to limit the amount you can learn. But based on what you learn, based on what structure you have, you can learn way faster in our environment. Okay, I feel like humans are more biased towards like, for example, we are more biased towards what do you call it? Navigation and place identification. So there's this thing called place cells, grid cells, heading cells, all this found in mice to like try to identify the location of where we are. And in fact, in neuroscience literature, there might be some other things like in your cortical columns of your neocortex, you might also have this place cells equivalent inside. So Numenta, Jeff Hawkins, has talked about all these place cells equivalent in the mini columns of the neocortex. And it seems to me that human knowledge and thinking is very biased to like place and position kind of thing. I mean, you think about it, like most knowledge you learn, like numbers, where do you put them on? You put them on a number line. It's like you have a certain place and you have a certain action which is based on like a velocity. So like position plus velocity, and you form a number line. Geography, you have like countries spatially separated in space. In fact, in a lot of things that we study, history, we have timeline. English, we have motions like to, fro, all this indicative of how we think. And I think we think with this kind of structure. We don't think in zeros and ones. We think with this kind of structure of movement and position. So this structure, I believe, is encoded in the structure of our heads already. So if we encode something like that in multi-agent systems, maybe it will work out. So these are just some of my thoughts. And the second thing, maybe the future of this algorithmic reasoning can go is memory systems. Because as you can see, like some problems like sorting, you need to store the entire memory of the entire array, which may not be present in the GNN because the GNN only stores the latent memory. So maybe what we need to do is store the order of all the elements in the array. We kind of need another module to the GNN, like maybe the memory module. So with that memory module, maybe you can solve more. So yeah, that is one of my thoughts as well. So yeah, I think that's the last slide. So now we have a discussion to see like if you have any points you want to bring up. Let me just end off with this slide here. So I really think the learning process looks like this. Yeah, so the algorithm part, the fixed processing like of your ears, cochlea, your vision systems, which is the retina and so on. All these have a fixed way of getting that representation. And then after we get that fixed representation, then maybe we use some form of neural network in order to form associations between different inputs and outputs. So the neural network is really for association between inputs and outputs. And we also associate them in some form of manner that is having some form of inductive bias, some form of structure, so as to minimize the amount of possibilities that we potentially need to generate. So this structure might be position, velocity, that kind of structure. Yeah, so all this, I'm not too sure exactly how the structure should be, but this is my best guess. Okay, I would like to end here. Yeah, if you have anything you want to share about, please feel free to say now. If not, thanks for coming, and I'll see you all again next time. Okay, bye-bye.